t-test. And t-test is when you have means. So you have lists of data that you can calculate a mean for, and you are figuring out how the average of one compares with the other. Okay? What we are doing now is chi-squared. So that's squiggly x, that's chi. And this is goodness of fit. Okay, we are doing the chi-squared goodness of fit. You use this when you have categories. And your data fits into categories. So your data is not 12.1 centimeters and 13.0 centimeters. It is how many items fit into this category. We had some seniors this year who did a chi-squared because they were looking at number of seeds germinated for a certain set of conditions. So I have some sample data for us to do a chi-squared on. Okay. Back in the fall, David did a project to see what color the bees were more attracted to. So we painted that board. He smeared honey or sugar water, something to attract the bees, and literally we just sat there and counted the bees. So here is our data. That over all of the times we did, 18 bees landed on red, 6 on blue, 13 on white, and 16 on yellow. So that is our observed data. Okay? So when we are looking at chi-squared, we are looking at observed data versus expected data. And we have our categories. And our categories were red, blue, yellow, and white. And I'm probably writing them down in a different order than they were. Almost. All right, so 18 and 6. And then yellow was 16 and white was 13. Okay, so we need to know the total. So that's easy. You just add them all up. So there are 53. So how many categories are there? 4. So we would expect equal distribution because we don't know anything that would say, oh, this percentage would fall on that. But like in your lab today, the company has said 13% of your M&Ms should be red. So your expected is based on the published percentages. So what is your null hypothesis going to be? That your expected is going to equal your observed. And your alternative hypothesis is just simply they're not equal to each other. Notice we don't have a mu because this isn't an average. Now, degrees of freedom is categories minus 1. So how many degrees of freedom do we have? 3. And we still use our same standard alpha level. What is your standard alpha level? 0.05. Now we have a chart that looks a lot like the chart we were using for t-test, except it says that it's for chi-square. Make sure you're using the right chart. So we have 0.05 and 3 degrees of freedom, so 7.815 is our critical table value. All right, so to put these in the calculator, go to second plus and clear all lists. Okay, now go into your stat and your edit. Okay, and put expected in one category, observed in the other category, and as long as you know which is in which, that's all that matters. Okay, so my observed is in list 1 and my expected is in list 2. So now I go to stat and go over to tests. This time I would say hit your up arrow because what you're going to is D, chi-squared, goodness of fit, and you actually get to it faster by going to the bottom of the list and up. But if you go down, you'll find it as well. And I said my observed was in list 1 and my expected was in list 2. How many degrees of freedom did we say we had? 3. And so let's calculate. And so I get a P of 0.09 and .38 for my chi-squared. So my chi-squared is less than my critical table value, and my P is greater than my alpha. So what do I do with my null? Fail to reject. So what do I do with my HA? Reject. So research hypothesis, well, it depends. Did we state B's have no preference? In which case we would support the research, or did we say B's would have a preference, in which case we fail to support the research? You have to go back and look and see what the research actually said. So the hypothesis was that the bees were more attracted to yellow. So did we support or not support the research? We did not support the research.